Welcome. Please settle in and allow this exhaustive technical narrative to guide you into sleep. If you appreciate this format, kindly support the project with a like and a subscription. The industrial genesis of a standard aluminum beverage container begins not within the confines of a factory, but deep within the geological strata of the Earth's crust. The primary precursor is bauxite, a sedimentary rock characterized by a high concentration of aluminum hydroxides. The procurement of this mineral involves extensive open-pit mining operations, where massive mechanical excavators remove the overburden to reach the ore. Once extracted, the bauxite is subjected to the Bayer process, a complex sequence of chemical refinements designed to isolate pure aluminum oxide, or alumina, from the surrounding silicates and iron oxides. This involves the digestion of the crushed ore in a caustic solution of sodium hydroxide at high temperatures and pressures. The resulting slurry is filtered and cooled, allowing for the precipitation of crystalline aluminum hydroxide, which is then calcined in rotary kilns to produce a fine white alumina powder. The transformation of this powder into a metallic state occurs within an electrolytic cell through the Hall-Héroult process. This is a high-energy industrial environment defined by the continuous flow of direct electric current through a molten bath of cryolite. The alumina is dissolved within this bath, where the electrolytic action breaks the powerful chemical bonds between the aluminum and oxygen atoms. Pure molten aluminum accumulates at the base of the cell, while oxygen is released at the carbon anodes, reacting to form carbon dioxide. The atmosphere of the smelting facility is a constant low-frequency hum of electrical transformers and the heavy ambient heat of the reduction cells. The liquid metal is periodically siphoned from the cells and transported in insulated crucibles to the casting department, where it begins its transition into a workable mechanical form. In the casting department, the aluminum is combined with specific quantities of alloying elements, such as magnesium and manganese, to enhance the structural strength and formability of the finished container. The metal is then cast into massive rectangular ingots, each weighing several thousand kilograms. These ingots represent a state of metallurgical potential, possessing a uniform grain structure that is essential for the subsequent rolling operations. The movement of these ingots through the facility is handled by heavy-duty overhead cranes and automated roller conveyors, moving with a slow, unvarying momentum that signifies the scale of the industrial logic at work. The next mechanical event is the hot rolling process, where the heated ingot is passed through a series of massive steel rollers. Each pass reduces the thickness of the metal while increasing its length, transforming the monolithic block into a continuous ribbon of aluminum. This is followed by cold rolling, a high-precision operation where the metal is processed at ambient temperatures to achieve the final exacting thickness required for the can body. During cold rolling, the metal undergoes work hardening, increasing its tensile strength and surface hardness. To facilitate this reduction, a thin film of specialized synthetic lubricant is applied to the surface of the metal, preventing adhesion to the rollers and ensuring a flawless reflective finish. The sound of the rolling mill is a persistent high-pitched whine, produced by the intense pressure of the rollers against the moving metallic substrate. The resulting aluminum sheet is then wound into massive coils, each containing several kilometers of material. These coils are the primary input for the beverage can factory. Before being shipped, each coil is subjected to a rigorous quality assessment, where laser sensors and ultrasonic detectors scan the surface for any microscopic imperfections or variations in gauge. The dimensional stability of the sheet is critical, as even a variation of a few microns could lead to mechanical failure during the high-speed stamping and drawing processes. The coils are organized within the warehouse, a sterile and silent environment where they await their entry into the automated production line. The logistics of transporting these coils involves specialized freight systems designed to manage the immense weight and sensitivity of the material. Each coil is secured within a protective cradle and encapsulated in a moisture-resistant film to prevent oxidation. The movement of the metal from the smelter to the rolling mill and finally to the can plant is a display of intermodal efficiency, governed by a global network of rail and maritime transport. The logic of the supply chain ensures that a constant flow of material is maintained, matching the output of the smelting cells to the intake of the stamping presses. At the threshold of the can factory, the coil is positioned on an unwinder mechanism. This device gradually unwinds the metal, feeding it into a pre-lubrication station where a precisely metered layer of wax-based lubricant is applied. This lubricant is essential for the cupping process, where the flat sheet will be transformed into a three-dimensional form. The movement of the aluminum into the factory is a slow, relentless progression, a river of silver light moving towards the mechanical intervention of the high-speed presses. The environment of the facility is characterized by the rhythmic pulse of the machinery and the steady, unvarying flow of the metallic substrate. The atmosphere of the plant is one of clinical precision. The air is filtered to remove particulate matter, and the temperature is stabilized to maintain the mechanical properties of the aluminum. Every movement within the system is monitored by sensors that transmit data on tension, speed, and thickness to a central control room. The logic of the system is absolute, functioning with a degree of mechanical regularity that ensures the continuity of the production line. The minerals, which existed for millions of years in a geological state, have now been systematically refined and rolled into a technical precursor for the container fabrication process. As this chapter concludes, the aluminum coil is fully integrated into the intake system of the factory. It represents a state of readiness where the metallurgical identity of the metal has been established, but its functional form has yet to be realized. The transformation from a flat sheet to a hollow cup is the next mechanical event in the sequence, requiring the application of immense hydraulic force within a specialized die set. The steady hum of the unwinder and the distant roar of the lubrication system form the acoustic backdrop to this preparatory stage, a testament to the industrial scale required to manufacture even the most common of objects. The process continues without interruption as the next coil is positioned for entry, maintaining the constant flow of material that sustains the life of the plant. The quality of the aluminum is verified by real-time analysis, ensuring that the chemical composition and mechanical grain are perfectly suited for the stresses of the drawing and ironing stages. The movement of the metal is a slow, relentless progression, a stream of industrial potential moving towards the complex mechanical modifications that follow. The state of readiness is now complete. The raw earth has been transformed into a technical substrate prepared for the intense mechanical transformations that define the life of the aluminum can. The introduction of the lubricated aluminum ribbon into the high-speed cupping press represents the first significant mechanical deformation in the manufacturing cycle of the beverage container. This stage is characterized by a transition from a continuous two-dimensional plane to a discrete three-dimensional form, a process governed by the rhythmic and relentless movement of heavy-duty steel die sets. The cupping press is a massive vertically reciprocating assembly anchored to the facility floor to dampen the immense vibrational energy generated by its operation. As the aluminum sheet is drawn into the press by a series of precision feed rollers, it enters a zone of extreme mechanical pressure where the metallurgical properties of the alloy are tested against the structural integrity of the hardened tool steel. The atmosphere surrounding the press is a dense sensory environment defined by the persistent metallic thud of the punch and the intermittent hiss of high-pressure air used to eject the newly formed components. The process begins with the blanking phase, a high-precision shearing action where the press forces a circular punch through the aluminum sheet. This action occurs simultaneously across multiple positions, typically producing a dozen or more circular discs with every single stroke of the press. The diameter of these discs is calculated with absolute precision to ensure that the volume of metal is sufficient to form the complete body of the can in the subsequent stages. The shearing of the aluminum produces a distinct, sharp acoustic signature, a sound that repeats hundreds of times every minute, forming the fundamental pulse of the cupping department. As the punch descends, the lubricating film applied in the previous stage ensures that the metal slides smoothly across the cutting edges, preventing the formation of burrs or surface irregularities that would compromise the structural integrity of the final product. Immediately following the shearing action, the press continues its downward stroke to initiate the drawing phase. The circular disc, now held securely between the die and a pressure sleeve, is forced through a forming ring. This mechanical intervention causes the flat disc to wrap around the punch, transforming it into a shallow, wide-diameter cylinder known as a cup. This transformation is a study in the plastic flow of metals, where the aluminum atoms are forced to rearrange themselves under the influence of compressive and tensile forces. The thickness of the metal remains relatively constant during this initial draw, but its geometry is fundamentally altered. The resulting cups possess a uniform height and a perfectly circular rim, representing the first recognizable stage of the container's physical identity. The mechanical logic of the cupping press is a closed-loop system of high-speed coordination. For every downward stroke that forms a set of cups, there is a synchronized upward stroke that clears the workspace and advances the aluminum ribbon for the next cycle. This advancement must be perfectly timed to a fraction of a millimeter to minimize the amount of leftover metal between the circular holes. The leftover material, known as the skeleton or scrap web, is pulled through the rear of the press by a secondary set of rollers. This skeleton is a fragile, lattice-like ribbon of aluminum that still carries the industrial lubricant. It is immediately routed through a series of overhead chutes toward a high-capacity scrap baler, where it is compressed into dense blocks to be returned to the smelting facility for remelting. This internal recycling loop ensures that the efficiency of the material usage remains at its theoretical maximum. As the cups are formed, they are ejected from the die sets by a blast of compressed air and fall onto a wide multi-lane conveyor belt located beneath the press. The movement of the cups away from the press is a fluid, chaotic progression that is quickly organized by a series of diverging guides. These guides distribute the cups into single-file rows, preparing them for transport to the next department. The sound of thousands of aluminum cups falling onto the conveyor and clinking against one another creates a continuous high-frequency rustle, a metallic white noise that blankets the cupping area. The environment is one of unvarying repetition, where the only change is the gradual unwinding of the aluminum coil at the intake. Inside the cupping press, the tool steel components are subjected to immense thermal and mechanical stress. To maintain their dimensional accuracy, a continuous flow of cooling lubricant is circulated through the die housing. This fluid not only manages the temperature, but also carries away any microscopic metallic fragments that could cause surface defects. The condition of the dies is monitored by a network of electronic sensors that detect even the slightest variation in the force required to form the cup. Any deviation from the established technical baseline triggers an automated alert, allowing for real-time adjustments to the press timing or the lubrication flow. This level of technical oversight ensures that every cup produced is a perfect duplicate of the one that preceded it. The journey of the cups from the press to the bodymaker is the final sequence of this chapter. The cups are transported via a network of air-assisted conveyors, where they float on a thin cushion of moving air to minimize surface friction. This transport system is a marvel of industrial logistics, winding through the upper levels of the facility to save floor space. The cups move in a steady silver stream, reflecting the overhead industrial lighting as they march toward the next stage of their evolution. The logic of the process is one of constant accumulation and distribution, ensuring that the bodymakers always have a sufficient reservoir of cups to maintain their high-speed operation. At this stage, the cup is merely a technical precursor. It possesses the necessary volume and metallurgical state, but it lacks the height and the thin-walled profile of a finished beverage can. It is a robust, shallow vessel that must now undergo the ironing process, a sequence of extreme mechanical stretching that will define its final structural characteristics. The atmosphere of the facility remains dominated by the rhythmic thumping of the cupping press, a constant reminder of the industrial force required to transform a geological mineral into a functional object. The process continues without hesitation, governed by the absolute logic of the manufacturing cycle. The state of the aluminum at the conclusion of this chapter is one of transition. The metal has been cut, shaped, and moved, yet its ultimate form is still many mechanical steps away. The internal grain structure of the alloy has been oriented by the drawing process, providing the necessary strength for the ironing stages that follow. The cups, organized in their disciplined rows, represent the successful application of reciprocating mechanical force. They are the building blocks of the production line, moving relentlessly toward the complex thermal and mechanical modifications that will eventually render them capable of containing pressurized liquids. The steady hum of the conveyors and the distant roar of the scrap baler form the acoustic backdrop to this ongoing industrial evolution. The progression of the shallow aluminum cup into the bodymaker represents the most intense phase of mechanical elongation and structural refinement in the manufacturing process. The bodymaker is a high-speed horizontal reciprocating machine that utilizes a series of tool steel ironing rings and a specialized punch to transform the thick-walled cup into a high aspect ratio cylinder. This transition is governed by the principles of plastic deformation, where the aluminum is stretched beyond its initial geometry while maintaining its molecular continuity. The environment surrounding the bodymaker is characterized by a persistent, rhythmic mechanical thrumming and the constant cascading flow of a water-soluble coolant and lubricant. The atmosphere is thick with a fine metallic mist, and the sound of the machine's stroke provides a hypnotic, unvarying cadence that signifies the transformation of the metallic substrate. As the cup is fed into the intake of the bodymaker, it is first subjected to a redraw operation. A primary sleeve captures the cup and holds it against the first die, while a central punch moves forward to reduce its diameter and increase its height. This initial stage establishes the final diameter of the can body, preparing it for the subsequent thinning of the walls. The movement is precise and fluid, occurring within a fraction of a second. Following the redraw, the punch continues its horizontal progression, forcing the aluminum through a series of 3 or 4 ironing rings of progressively smaller internal diameters. These rings are manufactured from tungsten carbide or other ultra-hard materials to resist the abrasive forces of the moving metal. The ironing process is a study in controlled friction and material flow. As the aluminum is forced through the narrow gap between the punch and the ironing rings, the wall thickness is reduced by more than 60% of its original gauge. This displacement of metal causes the can body to elongate significantly, stretching upward along the length of the punch. The base of the can, however, remains at its original thickness to ensure the structural integrity of the container's foundation. The physics of this process require a constant application of specialized coolant, which serves to reduce the thermal energy generated by the friction and to prevent the metal from adhering to the tool surfaces. This coolant is circulated in a continuous loop, filtered and chilled to maintain its technical properties. At the terminal end of the punch's stroke, the can body encounters the doming station. This assembly consists of a stationary die with a convex profile that corresponds to the internal geometry of the punch head. As the punch reaches its maximum extension, it presses the base of the aluminum cylinder against the dome die, creating the characteristic concave bottom of the beverage container. This arched geometry is essential for the can's ability to withstand internal pressure once it is filled with carbonated liquids. The formation of the dome is a decisive mechanical event, occurring at the precise moment before the punch begins its retaliatory stroke. The extraction of the can body from the punch is achieved through a mechanical stripper or a burst of compressed air. As the punch begins to move backward, the newly formed can, now tall, thin-walled, and reflective, is released and deposited onto a specialized transport system. Because the ironing process leaves the top edge of the can with an irregular, wavy perimeter known as ears, the container is not yet ready for the subsequent coating stages. These irregularities are the result of the metallurgical grain orientation of the original aluminum sheet, and they must be removed to ensure a perfectly uniform height. The movement of the can bodies away from the bodymaker is managed through a series of vacuum-assisted conveyors. These systems utilize a low-pressure environment to securely hold the lightweight aluminum cylinders against the moving belts, allowing them to be transported at high velocities towards the trimming station. The sound of the vacuum pumps and the steady metallic clinking of the cans form the acoustic signature of this department. The logic of the process ensures a continuous synchronized flow, where the output of multiple bodymakers is funneled into a singular stream of production. Inside the bodymaker, the technical oversight is absolute. A network of sensors monitors the force of each stroke, the temperature of the coolant, and the dimensional accuracy of the ironing rings. Any variation in the metal's resistance or a fluctuation in the lubricant's viscosity is detected in real time, allowing for micro-adjustments to the machine's timing. This constant feedback loop ensures that the millions of cans produced daily are identical in their wall thickness and structural strength. The environment remains one of intense calculated repetition, where the only variable is the relentless progression of the silver cylinders. At the conclusion of this chapter, the aluminum has been successfully disciplined into its final volumetric form. The cup has been stretched, ironed, and domed, resulting in a thin-walled vessel that possesses remarkable strength-to-weight characteristics. However, the container is still covered in a film of industrial coolant and possesses an unfinished top edge. The transition from a mechanical form to a clean, decorated product is the next stage of the journey. The steady hum of the bodymakers and the distant roar of the coolant filtration system continue to provide the soundtrack to this industrial evolution, a testament to the precision required to manipulate matter at such high velocities. The state of the aluminum is now one of structural completion but surface readiness. The metal has been hardened by the intense mechanical work, providing the tensile strength necessary for its future life as a pressurized vessel. The cans, marching in their disciplined rows, represent the successful application of horizontal reciprocating force. They move towards the trimmer, where their irregular edges will be systematically removed, marking the transition from the hot mechanical phase to the cold chemical and decorative stages of the manufacturing cycle. The transition of the elongated aluminum cylinders from the bodymaker to the trimming station marks the conclusion of the heavy mechanical deformation phase and the beginning of the surface preparation sequence. As the cans emerge from the bodymaker, they possess irregular, wave-like edges at their open end, a metallurgical phenomenon known as earing. This irregularity is the direct result of the anisotropic properties of the rolled aluminum sheet, where the metal flows more readily in certain directions relative to its grain orientation. To ensure that every container meets the exact height specification required for the subsequent necking and seaming operations, these irregular fringes must be systematically removed. The rotary trimmer is a high-precision machine designed to perform this task with absolute consistency, utilizing a set of circular steel blades that interface with the moving cans at high velocities. The containers are transported to the trimmer via vacuum-assisted conveyors, where they are organized into a single-file line. Each can is captured by a rotating mandrel that spins the cylinder at several thousand revolutions per minute. As the can rotates, a stationary or counter-rotating circular blade moves into contact with the upper perimeter of the aluminum. The blade shears the irregular ears from the body, leaving a perfectly smooth horizontal rim. This mechanical event is a display of extreme precision, where the tolerance for the can's final height is measured in fractions of a millimeter. The sound of the trimming department is a continuous high-frequency whirring, punctuated by the sharp metallic hiss of the vacuum systems that extract the aluminum rings. These rings, the trimmed scrap, are immediately evacuated through a network of pneumatic tubes and routed back to the recycling center to be compressed and remelted, maintaining the circularity of the production cycle. Once the containers have achieved their specified height, they are moved into the massive tunnel-like structure of the industrial washer. At this stage, the interior and exterior surfaces of the aluminum are still coated in a film of the water-soluble lubricants and metallic particulates generated during the ironing and trimming processes. This contamination must be entirely removed to ensure the proper adhesion of the decorative inks and the internal protective coatings. The washer is a multi-stage chemical treatment system, extending for dozens of meters and divided into several distinct environmental zones. The cans are placed onto a wide stainless steel mesh belt in a massive upright configuration, moving through the washer in a slow, unvarying mass flow. The first zone of the washer involves a high-pressure spray of a heated acidic solution. This chemical wash is designed to emulsify the oils and surfactants remaining on the metal, while simultaneously etching the surface of the aluminum to create a microscopic profile that facilitates coating adhesion. The sound within the washer is a constant cavernous roar produced by hundreds of high-velocity spray nozzles that saturate the moving cans from every angle. The chemistry of the wash is monitored in real time by automated sensors that measure the concentration of the acid and the temperature of the solution, ensuring that the etching process remains within a narrow technical range. Following the acidic wash, the containers progress through a series of rinsing zones. These stages utilize progressively purer water to remove all traces of the cleaning chemicals. The final rinse is conducted using deionized water, water that has been stripped of all mineral ions to prevent the formation of water spots or surface oxidation during the drying process. The movement of the water is managed by a series of powerful pumps that recirculate the fluids through a complex filtration system, removing the captured oils and metallic fines. The atmosphere within the washing department is one of high humidity and the sterile, clinical scent of the cleaning agents. The terminal phase of the washing cycle occurs within the dry-off oven. As the cans emerge from the final deionized rinse, they carry a thin layer of residual moisture that must be evaporated before the metal enters the decoration department. The dry-off oven is a high-capacity thermal chamber where heated air is circulated at high velocities over the moving containers. The temperature of the oven is calibrated to achieve rapid evaporation without inducing thermal stress in the thin aluminum walls. As the cans move through the oven, the moisture is transformed into vapor and exhausted through the facility's ventilation system. The containers emerge from the oven in a state of thermal and chemical readiness. Their surfaces are perfectly clean, dry, and microscopically etched, appearing as a sea of dull silver cylinders. The logic of the washing system is one of absolute consistency and environmental control. The speed of the mesh belt is synchronized with the output of the body makers and trimmers, ensuring that the flow of containers is never interrupted. The technical oversight of the washer is managed by a centralized control system that coordinates the flow of chemicals, water, and heat. This ensures that every individual can, out of the millions processed daily, undergoes the exact same sequence of chemical purification. The environment of the facility at this stage is characterized by the steady industrial rhythm of the pumps and the distant muffled roar of the drying fans. At the conclusion of this chapter, the aluminum container has been physically and chemically refined. The irregular ears have been removed, and the industrial lubricants have been replaced by a pristine, etched surface. The container is no longer a mechanical byproduct of the ironing press. It is a technical substrate prepared for the high-speed application of the brand identity and the internal protective barriers. The steady hum of the conveyors and the rhythmic movement of the mesh belt continue to provide the acoustic backdrop to this industrial evolution, a testament to the complex technical sequences required to manufacture a standard aluminum container. The state of the aluminum is now of readiness. The metal is clean, the dimensions are exact, and the surface is primed. The cans move toward the decorator, where they will be subjected to the high-speed application of multicolored inks and protective varnishes. This transition from a silver cylinder to a branded product is the next stage of the journey, moving from the domain of mechanical and chemical engineering into the domain of high-precision printing and surface chemistry. The emergence of the purified aluminum cylinders from the drying oven marks their entry into the most visually complex phase of the manufacturing cycle, the decoration department. At this stage, the containers are no longer treated as raw metallic substrates, but as canvases for high-speed, precision lithography. The transition from the washer conveyor to the decorator intake is managed by a sophisticated vacuum transfer system that reorganizes the mass flow of cans into a single high-velocity stream. The decorator is a massive rotary machine characterized by its extreme rotational velocity and the intricate synchronization of its mechanical components. The atmosphere in this section of the facility is defined by the pervasive scent of synthetic inks and solvents, accompanied by a rhythmic, high-frequency mechanical hum that signifies the simultaneous application of multiple color layers to thousands of containers every minute. The process begins as the cans are loaded onto individual rotating mandrels located on the perimeter of a large revolving wheel. Each mandrel is precision machined to match the internal diameter of the can body, ensuring that the container remains perfectly stable during the printing event. As the decorator wheel rotates, the cans are brought into contact with a series of inking stations. Unlike traditional printing, where colors are applied sequentially, the beverage can decorator utilizes a dry offset process. In this system, each color is first transferred from an ink reservoir to a set of distribution rollers, which then apply a thin, uniform film of pigment to a specialized printing plate. This plate contains the specific image or text for a single color of the brand design. The individual colors are then transferred from the plates onto a series of rotating rubber blankets. These blankets are mounted on a central drum known as the blanket wheel. As the blanket wheel revolves, it collects the various ink layers from each color station, effectively assembling the complete multicolored image on the surface of the rubber. The final mechanical event of the printing process occurs when the rotating can on its mandrel makes contact with the moving blanket. Through a single fluid revolution, the entire multicolored design is transferred from the rubber blanket to the exterior of the aluminum cylinder. The pressure of this contact is calibrated to within microns to ensure that the ink is applied with absolute clarity and without deforming the thin-walled container. Immediately following the application of the pigments, and while the can is still rotating on its mandrel, the container passes through the over-varnish station. This module applies a continuous transparent layer of protective coating over the freshly printed inks. The over-varnish serves a dual technical purpose. It provides a high gloss or matte aesthetic finish that enhances the visual appeal of the brand, and it creates a durable, low-friction surface that protects the pigments from abrasion during the subsequent high-speed handling and filling operations. The varnish is applied via a precision roller that makes brief tangential contact with the moving can, ensuring a perfectly uniform coating thickness across the entire longitudinal profile of the cylinder. The sound of the decoration department is a dense industrial symphony. The high-velocity whirring of the mandrels, the rhythmic clicking of the ink keys, and the steady pneumatic hiss of the vacuum transfer systems. The environment is one of extreme technical discipline, where the chemistry of the inks must be perfectly balanced against the mechanical timing of the rotary wheel. The viscosity and tack of the pigments are monitored in real time, as even a minor fluctuation in the ambient temperature of the facility can alter the flow characteristics of the synthetic resins. This level of oversight ensures that every container out of the hundreds of millions produced annually possesses a brand identity that is identical in color saturation and registration. Once the decoration and varnishing are complete, the containers must be removed from the mandrels for thermal curing. This is achieved through a mechanical takeoff system that utilizes a blast of compressed air to propel the cans from the rotating wheel onto the pins of a specialized conveyor known as the pin chain. The pin chain is a continuous loop of several thousand stainless steel pins, each designed to hold a single can by its internal base. The movement of the pin chain is synchronized with the output of the decorator, creating a long silver ribbon of containers that moves toward the entrance of the deco oven. The oven is a high-capacity thermal chamber where the synthetic inks and varnishes undergo a process of polymerization. As the cans move through the oven on the pin chain, they are exposed to a controlled flow of heated air that initiates a chemical reaction within the coatings. This reaction transforms the liquid pigments into a hard, durable, and chemically stable solid. The temperature profile of the oven is strictly regulated across several zones to ensure that the solvents are evaporated gradually, preventing the formation of surface bubbles or blisters. The sound of the oven is a deep atmospheric roar produced by the high-capacity recirculating fans that maintain the thermal equilibrium of the chamber. The transition through the deco oven is a moment of aesthetic and physical stabilization. As the cans emerge from the terminal cooling zone of the oven, the inks are no longer susceptible to smearing or damage. The containers appear transformed. The dull silver cylinders have been replaced by vibrant branded products with a reflective protective sheen. The cans are then transferred from the pin chain back onto a mass flow conveyor, where they are once again organized into wide multi-row configurations. The logic of the process ensures that the transition from the wet printing environment to the dry post-curing state is seamless and unvarying. The environment of the facility at this stage is characterized by the steady linear progression of the decorated containers toward the final internal treatment module. The logic of the manufacturing cycle is absolute, with the speed of the decorator perfectly matched to the capacity of the washing, ironing, and curing systems. Every movement is a display of industrial efficiency, where the application of pigment and heat is used to define the final identity of the aluminum can. The steady hum of the conveyors and the distant roar of the oven fans continue to provide the acoustic backdrop to this industrial evolution. The state of the aluminum is now a visual completion. The exterior of the container is fully decorated and protected by a cured layer of synthetic resins. However, the internal surface of the aluminum remains exposed and must be treated with a specialized barrier to prevent any chemical interaction between the metal and the liquid contents. The transition from the external decoration to the internal protection is the next stage of the journey. The cans, marching in their disciplined rows, represent the successful application of high-speed rotary lithography and thermal curing, moving relentlessly toward the final chemical and mechanical modifications of the production cycle. The transition of the externally decorated aluminum cylinders from the curing oven into the internal coating department represents a critical phase of chemical engineering, where the metallic substrate is provided with its final layer of functional protection. Although the exterior of the can has been successfully branded and varnished, the interior surface remains a raw, exposed aluminum alloy. If left untreated, the acidic or carbonated nature of the liquid contents would interact with the metal, leading to the corrosion of the container and the degradation of the product's chemical stability. To prevent this, a specialized synthetic barrier must be applied to the entire internal surface area. This process is governed by the principles of high-pressure atomization and occurs within a high-speed module known as the internal spray machine. The atmosphere in this section is characterized by the persistent, rhythmic pulsing of the spray lances and the sterile chemical scent of the liquid resins. The movement of the cans into the spray machine is managed by a vacuum-assisted star wheel that captures each cylinder and positions it with absolute precision. Unlike the decoration process, which utilizes a rotational transfer of ink, the internal coating is applied through the projection of a liquid lacquer into the stationary or rotating can body. As each container enters its designated spray station, a mechanical or electronic sensor verifies its presence, triggering the activation of a high-pressure spray lance. This lance is a specialized technical instrument equipped with a precision-machined nozzle designed to generate a specific spray pattern that covers the entirety of the internal walls and the complex geometry of the domed base. The atomization of the coating involves the conversion of a continuous stream of liquid resin into a fine mist of microscopic droplets. This is achieved through the application of hydraulic pressure or electrostatic force, which breaks the surface tension of the lacquer as it exits the nozzle. The coating itself is a complex chemical formulation, typically consisting of epoxy-based resins, vinyls, or modern biphenol-free alternatives, suspended in a volatile solvent or a water-based carrier. The viscosity of this fluid is monitored in real time, as it must remain thin enough to atomize perfectly, yet possess enough surface tension to adhere to the smooth aluminum surface without running or sagging. The sound of this department is a rapid-fire sequence of pneumatic pulses, a constant mechanical clicking as the spray guns fire hundreds of times every minute. The application of the internal coating is often conducted in two distinct stages to ensure total coverage. The first spray typically focuses on the base and the lower sidewalls, while the second stage targets the upper body and the flange area. This redundancy is essential for the structural integrity of the barrier, as even a microscopic pinhole in the coating could lead to a localized chemical reaction. The logic of the machine ensures that the volume of lacquer dispensed is calculated to within milligrams, maintaining the minimum coat weight necessary for protection while avoiding the accumulation of excessive material. This balance is managed by a centralized control system that adjusts the nozzle pressure and duration based on the flow characteristics of the resin. Immediately following the spray application, the containers carry a layer of wet, unpolymerized resin. They are then moved from the spray machine onto a wide mass flow conveyor that transports them toward the internal bake oven, or IBO. The movement is slow and unvarying, allowing the liquid coating to level across the microscopic etching produced during the washing stage. This leveling process ensures that the protective barrier is uniform in its thickness and free from surface irregularities. The sound of the conveyor is a low-frequency metallic rustle as thousands of wet cans move in unison toward the thermal treatment zone. The internal bake oven is a massive multi-zone thermal chamber designed to facilitate the polymerization of the synthetic resins. As the containers enter the oven, they are exposed to a controlled environment where heated air is circulated at high velocities. The thermal energy initiates a chemical cross-linking reaction within the coating, transforming the liquid lacquer into a hard, flexible, and chemically inert solid. This polymerization process is critical. If the temperature is too low, the coating will remain soft and permeable, while excessive heat could induce thermal degradation or cause the exterior pigments to discolor. The oven is divided into several temperature zones: heating, soaking, and cooling, each regulated to within a fraction of a degree. The atmosphere inside the oven is managed by a high-capacity extraction system that removes the vaporized solvents. These volatile organic compounds are routed through a thermal oxidizer, where they are incinerated at extreme temperatures to ensure environmental compliance. The sound within the IDO is a deep, continuous roar produced by the recirculating fans and the movement of the massive exhaust volumes. The logic of the system is a display of thermodynamic control, where the energy of the combustion is harnessed to create a permanent molecular bond between the aluminum and the protective resin. As the cans emerge from the terminal end of the bake oven, they undergo a rapid cooling phase to stabilize the coating. The containers are now physically and chemically complete. The internal surface is encapsulated in a transparent or gold-tinted barrier that is resistant to acids, salts, and carbonation. The transition from the wet spray state to the dry cured state represents the final chemical modification of the container's body. The cans are then organized into a single file line and moved toward the necking department, where the final mechanical shaping of the open end will occur. The environment of the facility at this stage is characterized by the steady, linear progression of the protected containers. The logic of the manufacturing cycle remains absolute, with the speed of the spray machines and the capacity of the bake ovens perfectly synchronized with the preceding ironing and decoration stages. Every movement is a display of industrial efficiency, where the application of pressurized chemistry and thermal energy is used to ensure the long-term safety of the future contents. The steady hum of the conveyors and the rhythmic pulsing of the spray lances continue to provide the acoustic backdrop to this industrial evolution. The state of the aluminum is now one of functional readiness. The exterior is decorated, the interior is protected, and the metallurgical structure is stabilized. However, the container still possesses a straight-walled profile and lacks the reduced diameter to accept the aluminum lid. The transition from a straight cylinder to a necked container is the next stage of the journey. The cans, marching in their disciplined rows, represent the successful application of high-pressure atomization and thermal polymerization, moving relentlessly toward the final mechanical adjustments of the production cycle. The movement of the cured and internally protected aluminum cylinders toward the necking department represents the final phase of high-speed mechanical shaping within the manufacturing cycle. At this stage, the container possesses its full height and decorated exterior, but it remains a straight-walled cylinder with a constant diameter from the base to the open rim. To facilitate the eventual application of the aluminum lid, which is significantly smaller in diameter than the can body to conserve material and enhance structural strength, the upper portion of the can must be systematically reduced. This process, known as necking, is a display of extreme metallurgical discipline, where the aluminum is forced to flow inward through a series of progressive mechanical reductions. The necking machine is a massive rotary assembly containing dozens of individual stations, each performing a microscopic fraction of the total diameter reduction. The atmosphere here is defined by the high-frequency rhythmic clicking of the transfer star wheels and the steady industrial hum of the vacuum manifolds. The physics of necking prohibit the reduction of the can's diameter in a single mechanical event, as the stress would cause the thin aluminum walls to wrinkle, crease, or collapse. Instead, the reduction is achieved through a sequence of incremental stages, often numbering between 11 and 14 distinct stations. As the cans enter the necker, they first pass through a waxer module, where a microscopic film of specialized synthetic wax is applied to the upper perimeter of the exterior. This lubricant is essential for minimizing the friction between the aluminum and the tool steel dies, preventing metal pickup or surface scoring that would compromise the visual and structural integrity of the container. The wax is applied via a rotating felt roller or a precision spray, ensuring a perfectly uniform distribution of the lubricant. Inside the necking machine, each individual station consists of a necking die and a corresponding inner centering sleeve. As the can is pushed into the die by a pneumatic or mechanical actuator, The die's tapered internal profile forces the aluminum to move inward. Simultaneously, the inner sleeve provides internal support to prevent the metal from buckling under the compressive force. Each stage reduces the diameter by only a fraction of a millimeter, gradually shaping the straight wall into a smooth, tapered neck. This process is a study in the plastic deformation of metals at high velocities, where the timing of the mechanical stroke must be synchronized within microseconds. The sound of the necking department is a persistent, dense clatter as thousands of cans are processed through the multiple stages of the rotary carousel. Between each necking stage, the cans are transferred via vacuum star wheels that hold the containers securely by their sidewalls. This ensures that the orientation remains perfectly vertical, preventing any eccentric deformation that would lead to a rejected unit. The logic of the machine is a continuous, staggered sequence where every rotation of the main turret produces a finished necked container. The technical oversight is managed by a network of electronic sensors that monitor the force required at each stage. If a container resists the die or experiences a structural failure, the system immediately identifies the specific station and activates a rejection gate at the exit of the machine. Following the completion of the necking stages, the container moves into the flanging station. This is the final mechanical shaping event for the can body. The flange is the outward projecting rim at the very top of the neck, which will eventually be interlocked with the lid during the seaming process at the bottling plant. To form the flange, a rotating tool or a stationary die expands the top few millimeters of the necked area, curling the metal outward to a specific horizontal angle. This geometry is critical. If the flange is too wide, it will interfere with the seaming operation, while an insufficient flange will result in a weak or leaking seal. The flanging process is a rapid, decisive mechanical expansion that marks the conclusion of the can's structural evolution. The movement of the necked and flanged cans away from the shaping department leads directly into the light tester, the final and most rigorous inspection module for the can body. Because the aluminum has undergone extreme stretching during the ironing phase and intense compression during the necking phase, there is a statistical possibility of microscopic fractures or pinholes developing in the metal. The light tester is a light-tight chamber where each can is placed over a high-intensity lamp. A series of ultra-sensitive photodiodes or high-speed cameras monitor the exterior of the can for any trace of light leakage. The sensitivity of this system is such that it can detect a hole smaller than a human hair. Any container that exhibits light penetration is instantly rejected via a high-velocity burst of compressed air, sending the defective unit into the scrap collection system for remelting. The logic of the light tester is an absolute safeguard, ensuring that only a physically perfect vessel proceeds to the packaging stage. The environment of the facility at this terminal stage is one of quiet electronic precision, contrasting with the mechanical violence of the ironing and necking departments. The steady rhythmic pulsing of the light tester's rejection gate is a testament to the uncompromising technical standards of the modern production line. At the conclusion of this chapter, the aluminum container has achieved its final geometric form. It possesses a decorated exterior, a protected interior, a tapered neck, and a precision-formed flange. It is no longer a raw metallic cylinder. It is a finished technical instrument, engineered to withstand internal pressures and provide a sterile environment for its contents. The steady hum of the conveyors and the distant clatter of the necking stations continue to provide the acoustic backdrop to this industrial evolution. The cans now move toward the final accumulation and palletizing area, where they will be prepared for their journey into the global logistics network. The state of the aluminum is now of total structural and aesthetic readiness. The metallurgical journey that began with the electrolytic reduction of alumina and progressed through the intense deformation of the bodymaker and the chemical discipline of the ovens has reached its technical climax. The cans, marching in their disciplined rows, represent the successful application of incremental rotary force and optoelectronic verification. They move relentlessly toward the palletizer, where the individual identity of the can will once again be subsumed into the organized mass of industrial distribution. The movement of the physically and chemically verified aluminum containers away from the light tester represents the transition from individual unit fabrication to bulk logistical organization. At this stage, the can bodies are finished products of the can-making facility, awaiting transport to a separate bottling or filling plant where they will be integrated with their liquid contents and final aluminum lids. The individual identity of each container is now subsumed into a massive, organized collection known as a pallet. This consolidation is governed by the principles of high-density accumulation and occurs within a fully automated palletizing module. The atmosphere in this terminal department is characterized by a continuous, rhythmic metallic rustle, a sound produced by the contact of thousands of lightweight aluminum cylinders moving in a state of laminar confluence. The accumulation table serves as the primary interface between the high-speed production lines and the discrete movements of the palletizer. This system utilizes a wide, low-friction plastic or stainless steel belt that allows the single-file stream of cans to expand into a multi-row configuration. As the cans move across the table, they are guided by a series of diverging rails that manage the back pressure of the line, preventing the thin-walled containers from being crushed or dented by the force of the units behind them. The movement is slow and unyielding, reflecting the massive throughput of the facility. The logic of the accumulation table is to act as a hydraulic buffer, ensuring that the palletizing system always has a sufficient reservoir of containers to maintain its operational rhythm. The palletizing process begins with the formation of a singular layer of cans. A mechanical sweeping arm or a set of pneumatic pushers moves across the accumulation table, organizing a specific number of containers into a precise rectangular matrix. This matrix is calculated to perfectly match the dimensions of a standard industrial pallet, maximizing the spatial efficiency of the transport volume. Once the layer is formed, a high-capacity overhead gantry or a specialized lifting head, often utilizing a vacuum-assisted surface plate, descends to capture the entire group of cans. The lifting head secures several hundred units at once, moving them through a horizontal or vertical arc to deposit them onto the waiting pallet. The foundation of this organized mass is typically a wooden or plastic pallet, which is positioned within a central elevator system. To maintain the structural stability of the growing stack and to prevent direct metal-to-metal contact between the layers, an automated insertion mechanism places a layer sheet or tier sheet on top of each completed layer. These sheets, manufactured from corrugated cardboard or high-density polyethylene, act as a frictional stabilizer and a protective barrier. The sound of the palletizer is a complex industrial symphony, the high-pitched whine of the vacuum pumps, the rhythmic thud of the layer sheet feeder, and the deep atmospheric hum of the gantry motors. As the stack reaches its final height, often consisting of nearly 20 individual layers and containing several thousand aluminum units, the completed pallet is transferred from the elevator onto a heavy-duty roller conveyor. This conveyor transports the unstable stack toward the rotary strap wrapping module. At this stage, the pallet is highly susceptible to shifting or toppling, and its movement is governed by slow acceleration motor drives to ensure a smooth progression. The strap wrapper is a specialized machine that utilizes a rotating arm or a revolving turntable to apply multiple layers of thin, high-tension polyethylene film around the exterior of the pallet. The application of the strap wrap is a hypnotic circular progression. The film dispenser moves vertically along the height of the pallet as it rotates, creating a spiral pattern that binds the aluminum containers, the tier sheets, and the pallet base into a single, rigid monolithic block. This encapsulation provides the centripetal force necessary to withstand the kinetic stresses of global transit, while also protecting the sterile interiors of the cans from atmospheric dust and moisture. The sound of the wrapping process is a persistent, high-pitched whine as the plastic film is pulled through the tensioning rollers, accompanied by the low rumble of the rotating turntable. Following the encapsulation, the pallet moves to the automated labeling station. Here, a thermal transfer printer generates a logistical tracking label containing a unique identification code, the date of manufacture, the alloy batch number, and the destination coordinates. A pneumatic applicator arm presses the adhesive label onto the exterior of the strap wrap. This label serves as the digital link between the physical object and the global supply chain management system, allowing the facility to track the performance of the containers across their entire life cycle. The movement of the labeled pallet continues toward the terminal end of the conveyor line, where it is finally removed by a high-capacity forklift or an automated guided vehicle. The warehouse environment is a vast, climate-controlled space where thousands of pallets are stored in high-density racking systems. The atmosphere is one of profound stillness, contrasting with the intense heat and mechanical violence of the hot end of the factory. The pallets are organized according to a strict logistical logic, awaiting the arrival of intermodal shipping containers. The transition from the factory floor to the warehouse represents the completion of the structural manufacturing cycle. The raw materials that began as bauxite and alumina have been systematically transformed into thousands of identical, high-quality technical instruments, now securely bound and ready for their functional life in the marketplace. The state of the aluminum is now of total logistical readiness. The containers have survived the intense mechanical deformation of the bodymaker, the chemical discipline of the ovens, and the exhaustive scrutiny of the light tester. They are no longer individual metallic forms. They are part of a synchronized industrial flow moving toward the bottling plants where they will be integrated with the final component of the container system, the aluminum lid. The steady hum of the facility remains an unyielding backdrop to this ongoing evolution of matter, a testament to the complex technical sequences required to manufacture even the most common of objects with such absolute consistency. The production of the aluminum lid, technically referred to as the end, constitutes a distinct and highly specialized industrial sequence that occurs independently of the can body manufacturing line. While the body of the container is designed for extreme elongation and thin-walled efficiency, the end must possess a higher degree of structural rigidity to withstand the internal pressure of carbonated contents and the mechanical stresses of the opening event. This requires the procurement of a different metallurgical substrate, typically a 5000 series aluminum alloy characterized by a higher magnesium content. The fabrication of the end is a study in high-precision stamping and multi-stage mechanical conversion occurring within a facility environment defined by the rapid, percussive cadence of high-speed presses and the intricate movement of thousands of small metallic components through a network of overhead chutes. The process begins with the introduction of a wide, high-strength aluminum coil into the shell press. This coil is pre-coated on both surfaces with a specialized organic protective barrier, ensuring that the interior surface remains chemically inert and the exterior surface is prepared for the eventual application of identifying codes. The shell press is a massive, vertically reciprocating machine that performs the dual action of blanking and drawing. In a single stroke, the press shears a circular disc from the moving ribbon of metal and immediately forms it into a shallow, cup-like geometry known as a shell. The logic of this operation is one of massive parallelism, where a single press stroke can produce dozens of shells simultaneously. The sound of the shell press is a deep, rhythmic thrumming that forms the acoustic foundation of the end-making department. Following the initial formation, the shells are routed to the curler. As the shells move through this rotating mechanical module, the outer edge of the aluminum is systematically folded inward to create a rounded perimeter. This curl is a critical geometric feature, as it will eventually provide the necessary volume of metal for the double seam operation at the bottling plant. The curling process is a display of centrifugal precision, where the shells spin at high velocities against a stationary or counter-rotating die. The environment in this area is characterized by a persistent high-frequency metallic rustle as the shells are funneled toward the next stage of their evolution. The heart of the lid manufacturing process is the conversion press, a highly complex multi-station machine where the shell is transformed into an easy open end. This transformation involves a series of incremental mechanical modifications performed in a continuous, high-speed sequence. The first stage within the conversion press is the formation of the integral rivet. Unlike traditional mechanical joining, which requires a separate fastener, the aluminum lid utilizes a portion of its own material to create the attachment point for the tab. A specialized set of dies displaces a small circular area of the aluminum in the center of the shell, creating a bubble or button. This button is then reduced in diameter and increased in height through a series of secondary strokes, resulting in a perfectly formed vertical rivet that is still a contiguous part of the lid's molecular structure. Simultaneously, a separate production line, known as the tab line, fabricates the stay-on tab from a narrower coil of aluminum. The tab is a masterpiece of complex mechanical folding and stamping. Over a dozen distinct stages, the metal is punched, folded to create reinforced edges, and shaped into the familiar geometry that provides the consumer with the necessary leverage to open the container. The tab line operates with a degree of mechanical ferocity, where the metallic ribbon is transformed into thousands of individual tabs every minute. These tabs are then transported via an air-assisted conveyor to the conversion press, where they meet the waiting shells. The integration of the tab onto the shell is a high-precision assembly event. The tab is positioned over the integral rivet, and a final staking stroke flattens the head of the rivet, permanently securing the tab in its terminal location. At this same moment, the press performs the scoring operation. A high-precision die with a microscopic cutting edge is pressed into the surface of the aluminum, creating a U-shaped or smile score line. This score line intentionally weakens the metal to a specific depth, calculated to within microns. The logic of this engineering is to ensure that the lid will rupture predictably when the tab is lifted, while maintaining enough structural integrity to prevent spontaneous failure during transit or storage. Following the mechanical conversion, the ends are routed to the compound liner module. This is a critical chemical intervention where a liquid sealing gasket, typically a synthetic rubber or a specialized polymer emulsion, is applied into the channel created by the curl. The ends are rotated at high speeds beneath a precision-timed nozzle that dispenses a single continuous bead of the compound. The centrifugal force ensures that the liquid is distributed evenly around the entire perimeter of the curl. This material is essential for the eventual hermetic seal of the beverage container. When the lid is seamed onto the body, this material will act as a gasket, filling any microscopic voids and preventing the escape of pressurized gases. The newly applied compound must be thermally stabilized within an induction or gas-fired oven. As the ends move through the oven in a dense, overlapping configuration known as a shingle, they are exposed to a controlled temperature profile that evaporates the water or solvents from the emulsion, which transforms the liquid bead into a resilient, elastic solid. The atmosphere inside the compound oven is one of quiet, intense heat, and the sound is a steady, muffled roar produced by the recirculating fans. The transition through the oven marks the conclusion of the chemical and mechanical modifications of the aluminum end. The final stage of the lid manufacturing process is the automated inspection and packaging. Each end is passed through an optoelectronic scanner that verifies the integrity of the score line, the placement of the tab, and the consistency of the compound liner. Any unit that deviates from the established technical standard is immediately rejected via a high-velocity burst of compressed air. The successful ends are then organized into long cylindrical tubes known as sleeves, which are wrapped in protective paper or plastic film. These sleeves are then palletized and prepared for transport to the bottling facility, where they will finally meet the aluminum bodies produced on the main production line. The state of the aluminum end at the conclusion of this chapter is one of functional readiness. It represents the successful application of integral riveting, high-precision scoring, and chemical gasket deposition. The story of the aluminum container is now complete in its individual components. The body and the end have been fabricated through separate but equally exhaustive technical sequences. The logic of the process now moves toward the terminal event of the container's life cycle, the integration of the liquid product, the mechanical seaming of the lid, and the final delivery into the global marketplace. The steady hum of the facility and the rhythmic clicking of the conversion presses remain the unyielding soundtrack to this industrial evolution, a testament to the absolute consistency required to manufacture billions of identical components. The movement of the individual components, the thin-walled can body and the high-strength aluminum end, toward the terminal synchronization of the bottling facility represents the final stage of structural integration. This phase is characterized by the high-velocity union of matter and liquid occurring within a sterile industrial environment defined by the relentless cadence of rotary filling and seaming carousels. As the pallets of can bodies are depalletized and organized into a single file stream, they enter the filling department, where they undergo a final sequence of atmospheric purging and volumetric integration. The atmosphere here is a dense sensory landscape, saturated with the rhythmic hissing of pressurized gases, the cascading sound of cooling water, and the steady, high-frequency clinking of thousands of metallic units moving in a state of laminar confluence. The filling process is governed by the principles of isobaric equilibrium, ensuring that the liquid product is transferred into the aluminum cavity without the loss of carbonation or the introduction of oxidative contaminants. As each can enters the filling carousel, a centering bell establishes a hermetic seal against the flange. A vacuum pump extracts the ambient air, replacing it with a controlled atmosphere of carbon dioxide. Only when the internal pressure of the container matches the pressure of the product reservoir does the liquid flow begin, directed down the internal walls of the can by a specialized spreader to minimize turbulence. The logic of the filling machine is an absolute mechanical loop, where the volume of every container is verified to within a fraction of a milliliter. Immediately following the filling event, the can moves toward the seamer, where it meets the aluminum end. The double seam is the definitive mechanical bond of the beverage industry, a two-stage folding process that creates a permanent gas-tight seal without the use of adhesives or heat. In the first operation, a specialized seaming roll captures the curl of the lid and the flange of the can, folding them together into a loose interlocked structure. The second operation then applies an immense flattening force, compressing the metal and the synthetic compound liner into a solid, hermetic, 5-layer sandwich of aluminum. This mechanical event occurs in a fraction of a second, yet it defines the structural integrity of the container for its entire functional life. Following the seaming operation, the filled containers progress through a warming or pasteurization tunnel. This stage involves the application of a precisely controlled temperature profile to ensure the biological stability of the contents and to prevent the formation of atmospheric condensation on the exterior surface during packaging. As the cans emerge from the tunnel, they are dried via high-velocity air knives and moved toward the secondary packaging modules. Here, they are organized into cardboard trays or shrink-wrapped packs prepared for their journey into the global logistics network. The logic of the process is a transition from individual fabrication to consumer-ready distribution. The climax of the container's functional existence is the phenomenon of the consumer opening. This is a moment of sudden thermodynamic transition. As the consumer lifts the stay-on tab, the mechanical leverage is transmitted to the integral rivet, causing the aluminum to rupture along the predefined score line. The internal pressure is suddenly released into the lower pressure environment, producing the characteristic acoustic crack of the aluminum and the subsequent hiss of escaping carbon dioxide. This release signifies the successful performance of every technical sequence described in this history, from the smelting of the alumina to the precision of the double seam. Once the contents have been consumed, the aluminum container enters the final and most important phase of its life cycle, the infinite circularity of recycling. Unlike many other materials, aluminum is a permanent element that does not degrade in quality during the recycling process. The empty can is collected, shredded, and melted in a furnace, effectively returning to the state of a molten alloy. Because remelting aluminum requires only 5% of the energy necessary to produce virgin metal from bauxite, the circularity of the can is an industrial triumph of energy efficiency. Within 60 days, the molecules of the consumed can be back on a retail shelf in the form of a brand new can. The logic of the aluminum matrix is a perpetual loop. The matter is never destroyed, it is merely transformed through the continuous application of thermodynamic and mechanical force. The steady hum of the smelting furnace, the rhythmic pulse of the cupping press, and the sterile roar of the bottling plant form the unvarying soundtrack to this ongoing industrial evolution. The story of the standard aluminum can is a testament to the absolute consistency and technical discipline of the modern world. A journey of silicon, magnesium, and aluminum through the fires of technology and the requirements of global commerce. The technical history of the aluminum container concludes here, at the threshold of its next reincarnation. The vessel that was once a river of molten alloy is now a shred of scrap, ready to be melted and formed once more. The circle is closed, and the movement of the metal continues without beginning and without end in the silent rhythmic service of global industry.